Linked lists are one of the fundamental data structures consisting of individual nodes of data interconnected by pointers. They provide a dynamic and efficient way to organize information. Each node contains stored data as well as the reference to the following node in the sequence, resulting in serial arrangement of information. In a linked list, the head pointer references the first node and serves as the user's entrance to the list. At its opposite end, the final node points to null, signifying the absence of stored information at the end of the linked list. Together, the head pointer, the null pointer, and the individual nodes make up the linked list data structure. In this introductory level video, we aim to demonstrate the basics of the linked list divided into 3 sections. We will first introduce the 4 variants of the linked list. Then, we will tackle the basic operations performed on linked lists, search, insertion, and deletion, as well as discuss their efficiencies. Later, we will examine the advantages and disadvantages of using linked lists as opposed to other data structures. Timestamps are below for each section. At the end of the video, you should have a good grasp on the fundamentals of a linked list and be able to implement them in your own code. The first and most common variant of the linked list, a singly linked list, connects its nodes in one direction, forming a unidirectional chain. Each node in this type consists of 2 attributes, its data and the address of the following node in the list. This address is typically in the form of a pointer and enables forward traversal through the list, as the next node points to the one after, and that one to the one after that, and so on. As a result of its one-way structure, while traversing through a singly linked list, previous nodes are unable to be easily referenced again once already passed by. The only way to access previous nodes is by restarting the traversal process from the beginning at the head node. Despite the absence of backwards traversal capabilities, singly linked lists benefit from lower memory usage and simplicity of design, resulting in reduced memory overhead and rapid operation performance. In order to address the backwards traversal problem, doubly linked lists contain another pointer, a previous pointer. The addition of the previous pointer along with the next pointer allows the doubly linked list to be traversed in both directions, forwards and backwards, as it connects the current node with 2 neighbor nodes, its next and previous nodes. This bidirectional connectivity allows for flexible traversal at the cost of requiring extra memory space per node to store that additional previous pointer. Doubly linked lists are typically chosen in scenarios where implementing bidirectional traversal significantly optimizes execution time, or when increased memory usage is not a concern. Circular linked lists further augment singly and doubly linked lists in a small but crucial way. Singly and doubly linked lists have clearly defined beginnings and ends, denoted by the head pointer and the final null pointer. The final null pointer serves as the break condition while traversing the linked list. Reaching the null pointer signifies that all nodes have been accessed and traversal is complete. Circular linked lists make use of this ending pointer to instead wrap back around and point towards the head node. This allows for continuous iteration through the linked list, as the end leads right back to the beginning. For doubly circular linked lists, in addition to altering the ending pointer, the head node's previous pointer, once similarly pointed to null, now wraps around and points to the end node, creating a bidirectional circular structure. Circular linked lists are helpful for data management in circular queues. However, without a proper termination condition, circular linked lists are in danger of infinite traversal loops. Altogether, singly circular, and doubly circular linked lists are similar in structure and characteristics, with minor modifications between the 4. For the remainder of this video, we will be concentrating on singly linked lists as they are the most commonly encountered variant. If there is enough demand to also include doubly linked lists and circular linked lists, we can discuss those in a follow-up video. But for the most part, the fundamentals of the singly linked list generally translate to the other variants as well. Let's explore some fundamental operations on a linked list, starting with the search operation. Given a desired target, denoted here by the character C, find its location in the linked list. To accomplish this, we traverse through the list starting at the head node. For every node, we compare its data against the target. If the current node's data does not match the target, we move on to the following node, which is referenced by the current node's next pointer. This next node becomes the new current node, and we compare again. Repeat this iterative process until either the target is found in the list or we exhaust all nodes. The search operation has a time complexity of O of n, where n is the number of nodes in the list. In the worst case, the target node exists at the end of the list, requiring iteration through every node in the linked list before reaching the target. Or the target node does not exist, requiring iteration through the entire linked list to verify. The second operation is insertion. Depending on the desired insertion position in the linked list, this operation is performed differently with 3 variants. Insertion at the beginning of a linked list requires redefining the head pointer. First, create the new node and set its next pointer to the current head node. Then, reassign the head pointer of the linked list to the newly created node. This effectively makes the newly created node the new head of the list, which will be accessed first in the sequence. Insertion at an index of a linked list requires more steps. Let's insert a node between nodes C and D. Iterate through the linked list until node C, the left node, is reached. Again, create the new node. This new node's next pointer is set to point toward node C's next node, in this case, node D, effectively placing the new node before node D in the list, fulfilling 1/2 of the insertion requirement. Then, node C's next pointer is assigned to the new node, placing the new node after C. Now, this new node is located between nodes C and D. Insertion at the end is relatively straightforward. Iterate through the list until the end node is reached. Create the new node. Then, connect the next pointer of the last node from null to the newly formed node. This incorporates the new node as the last node of the linked list. Insertion has a time complexity of O of 1 when inserting at the head, but also has a general time complexity of O of n. In the worst case, the insertion point is set at the end of the linked list, requiring iteration through the entire linked list. Finally, deletion. Careful handling of deletion is required in order to maintain the list's integrity. Let's delete the red nodes that we have added here. When deleting the first node of a linked list, it is crucial to adjust the head pointer properly. Prematurely removing the first node could eliminate access for the rest of the list. First, reassign the head pointer to the second node in the list. This will be our new first node after the deletion operation. Then, the first node can be safely removed. To delete a node at a specific index in the linked list, it is essential to keep track of 2 nodes, the target node and its previous node. Iterate through the list, both the previous node and the target node. Make sure that the previous node is always 1 node behind the target node when iterating. Once the target node reaches the desired deletion index, here's where the previous node comes into play. Update the next pointer of the saved previous node from the target node to the target node's next node. This effectively removes the target node from the list, since the pointers have been updated to bypass the target node. Deletion of the final node of a linked list also requires iterating through the list while monitoring the target node and its previous node. Once the last node has been reached as the target node, similarly update the previous node's next pointer, this time from the end node to null. Without any pointer to reference the end node, it is deleted from the list. The previous node now points to null, signifying that it is the last node in the list. Again, deletion has a time complexity of O of 1 when deleting the head node, but also has a general time complexity of O of n. In the worst case, the deletion of the final node requires iterating through the entire linked list. In general, the time complexity of linked list operations are directly related to the size of the list. Larger lists have more nodes, which means more time required to iterate through the list. On the other hand, for its space complexity, all operations are O of 1, since no extra storage is required. Using our understanding of the time and space complexities, we will now discuss the benefits and drawbacks of using a linked list. Discussions about linked lists often contrast their advantages and disadvantages with those of a similar data structure, arrays. Below is an illustration of both a linked list and an array, as well as their respective memory blocks. Both data structures store information linearly and are ordered. However, they have differences regarding their memory allocation properties and operation performance. Depending on the desired application, either data structure could be shown as preferable. The first advantage of linked lists is the usage of dynamic memory allocation. For linked lists, memory is allocated when needed, such as when a new node is inserted. Linked lists are able to grow and shrink during runtime, as required by the program, allowing for flexible implementation. In contrast, array memory is statically allocated during compile time, disallowing insertion beyond the reserved amount at runtime. Another advantage regarding the memory usage of linked lists is that the nodes are stored non-contiguously. The next pointer of each node retrieves the subsequent nodes regardless of their relative memory addresses. Arrays, on the other hand, require usage of contiguous sections of memory. Each element is stored sequentially. This could be detrimental in a scenario where there exists a sufficient amount of memory needed to instantiate a given array. However, said memory is non-adjacent. Linked lists are preferable in this case to avoid costly reshuffling of memory. One feature missing from linked lists is random access. Without the ability to directly access specific nodes without sequential iteration, linked lists lack the ability to randomly select an element, as opposed to arrays where any element can be indexed immediately, allowing for random access. Regarding operations, linked lists perform better insertion and deletion due to its dynamic and non-contiguous memory allocation, while performing worse in search due to its sequential structure. On the other hand, arrays perform inefficient insertion and deletion due to its contiguous memory allocation, while excelling in search due to indexing. Overall, deciding between using a linked list or an array requires understanding the respective strengths and weaknesses of both data structures, as well as the problem at hand. However, as a rule of thumb, linked lists are ideal for larger, non-constant datasets, while arrays are ideal for smaller, non-variable datasets. Linked lists are a powerful structure to organize and maintain data, useful in a multitude of programming contexts. By understanding their structure, operations, and strengths, linked lists provide an invaluable tool to the developer toolbox. Hey everyone, I hope you learned something from this video. If you did, definitely consider subscribing. We plan to release more videos on data structures and algorithms, some machine learning topics, and maybe some lead code problems too, so be on the lookout for those. And if you have any suggestions for future topics that we could cover on this channel, feel free to leave them down below in the comment section. Thanks for watching.